Today, we're diving into the incredible math that literally secures our entire digital world. But this isn't just a math lesson. It's also a story with a twist, a story about a secret back door, one that was allegedly built by the NSA, and how it almost broke everything. So here's the central question, the one that kicks off our whole story. How could something so small, a couple of supposedly random numbers, threaten the safety of, well, everyone online? To really get that, we have to rewind a bit and look at the system it was all built on. A true giant of cryptography that was, frankly, starting to get old. You see, for decades, one brilliant idea protected almost everything. But its time was running out. The mathematical trick it relied on was getting easier and easier for computers to solve. That idea is called public key cryptography. Think of it like a special padlock. I can give everyone a copy of my public key, and they can use it to snap that lock shut on a message. But only I have the private key that can open it. It's what we call a trapdoor function. It's super easy to go one way, locking the box, but it's nearly impossible to go backwards and open it unless you have that secret key. The classic example that everyone used for years was the RSA algorithm. Now, all of this magic happens in a special kind of math world called modular arithmetic. But honestly, you can just call it clock math because you already know how it works. If it's 10 a.m. and you have a 4-hour meeting, it's not 14 o'clock, right? It's 2 o'clock. The numbers just wrap around when they hit a certain point. It's a simple concept, but it's totally crucial for keeping the numbers in cryptography from getting out of control. So let's see this in action, right? Let's say we pick two prime numbers, 13 and 7. That gives us our clock, which wraps around at 91. And our public key is the number 5. We turn the message cloud into numbers. Now, to encrypt the first letter C, or 67, we just multiply 67 by itself 5 times, remembering to use our clock math. The final result is 58. You do that for every letter, and suddenly, cloud becomes this jumble of numbers that looks totally meaningless. And that right there, that's RSA's trapdoor. The easy part? Multiplying numbers together to scramble the message. A computer can do that in a heartbeat. The hard part, the thing that makes it secure, is going the other way, factoring. If all you know is the public number 91, it's really hard to work backwards and figure out it came from 13 times 7. Now imagine instead of 91, that number is hundreds of digits long. And right there, that's the problem. We're just getting too good at factoring. As our computers get more and more powerful, the only way to keep RSA safe is to use bigger and bigger numbers. That's maybe okay for a giant server farm, but it's a huge problem for your phone or your smartwatch or any little device. It was becoming an arms race, and it just wasn't sustainable. We needed a harder problem. And this search for a fundamentally harder problem led to a massive breakthrough. It was time for a new hero to enter the stage, elliptic curve cryptography. So elliptic curve cryptography, or ECC, is also a public key system, but it's playing a totally different game. It's not based on simple factoring. It's based on the weird, almost magical properties of points on these strange-looking curves. It's a kind of invented math, where if you add 2 points on the curve together, you get a third point that seems to be in a completely random new spot on that same curve. And this gives us our new, much stronger trapdoor. So imagine you pick a starting point on the curve. Let's call it P. It's incredibly easy for a computer to add P to itself, say, 1 trillion times, and land on a final point we'll call Q. But, and this is the whole secret, it's basically impossible for anyone else, even if they know your starting point P and your final point Q, to figure out that your secret number was 1 trillion. That is a way, way harder problem to solve. Exactly how much harder are we talking? Well, cryptographer Arjun Lenstra put it in pretty stark terms. He calculated that to break just one 228-bit elliptic curve key, you would need enough energy to boil every single ocean on Earth. That's just staggering. So here's the payoff, plain and simple. To get this same level of security that RSA needs a key over 2,000 bits long for, ECC only needs 228 bits. That's not just an improvement, that's a revolution in efficiency. And this incredible efficiency isn't just a cool thing for mathematicians to talk about. It is the fundamental reason that ECC now powers pretty much the entire modern web. So where is all this math hiding? Everywhere. That little padlock icon in your web browser? That's ECC. Your secure messaging apps, cryptocurrencies, all those smart devices in your house. Not to mention critical financial and military communications. Yep, they all depend on the compact power of ECC. Because it works so well, ECC quickly became the new gold standard. It was adopted by major standards organizations, including the one that sets the rules for the entire financial industry. We're talking about the system trusted to protect trillions of dollars. And it isn't just about smaller keys, it's also about raw speed. If you're creating a digital signature, the elliptic curve version can crank out 23 signatures in the time it takes the old RSA version to do just one. That is a massive performance boost. And hey, if you want a perfect high-stakes example, just look at Bitcoin. The security that protects every single Bitcoin wallet is pure ECC. Your public address, the one you can share with anyone, is just your secret private key multiplied by a standard starting point on the curve. It's that beautiful one-way trapdoor that makes sure only you can ever touch your money. So we have a faster, stronger, and way more efficient type of cryptography securing the planet. Great story, should end right there. But it doesn't, because a huge shadow was cast over all this amazing tech by the one agency you'd think would be its biggest champion, the NSA. And this gets us to the twist in the tale. We can trust the math. The math is sound. But what if you can't trust the people who are writing the rulebook for how to use the math? At the very center of this storm is something with a really clunky name, dual_EC_DRBG. It was a standardized way to generate random numbers, which are absolutely vital for creating strong keys. But right from the start, cryptographers saw a huge red flag. It was unbelievably slow, like 1,000 times slower than other methods, for no good reason. The way this standard worked was by using two public points on an elliptic curve. We'll just call them P and Q. Anyone who used this standard had to use these exact same 2 points. They were published by the National Institute for Standards and Technology, or NIST, and the assumption was that they were just two randomly chosen, totally unrelated points. But what if they weren't random? What if there was a secret mathematical link connecting them? What if Q was actually just P multiplied by some secret number? Let's call it E. Well, the NSA, who helped write the standard, were the ones who generated those points, and they never, ever explained how. And the trail of breadcrumbs just got worse from there. Cryptographers were shouting about this potential backdoor way back in 2007, and then the Snowden leaks revealed documents that suggested the NSA had paid a security company $10 million to make this one flawed standard the default option in their software. Because if the NSA knew that secret number E, they could break the trapdoor. They could predict all the random numbers and completely defeat the encryption of anyone using it. It's a pretty chilling reminder that even the most powerful mathematical lock is only as good as the person who designed it. And it leaves us with one final, really unsettling question. In this huge, complicated world of digital secrets, who can we really be sure is holding the keys?